So there are different types of solutions. You can have a solution between any combination of physical states or phases. So you can have a solution composed of two gases, a solution composed of two solids. That kind of seems, how would you do that? Well, it'd probably involve heating them up to melt them so that they could mix together and then cooling it down. Metal alloys such as brass are homogeneous mixtures of different metals. They are solid solutions. And what we're more familiar with are liquid solutions, where you can have a gas, a liquid, or a solid that's dissolved in a liquid. So examples would be club soda. Vodka is ethanol and water. Ethanol is a liquid. Seawater would be salt and water. When we talk about an aqueous solution, the word aqueous tells us that the solvent is water. And water is like the universal solvent. It's a very, very common solvent, and so lots of aqueous solutions. Water dissolves a lot of things, but it will not dissolve everything. Not everything will dissolve in water. Solubility is a term describing how much of a substance will dissolve in a particular amount of solvent. And the solubility depends on several things, including the tendency towards mixing and the types of intermolecular forces. So here we have some club soda. It's got carbon dioxide and water. And the carbon dioxide has limited solubility in the water. So as this sits, the carbon dioxide is going to come out of solution, and that's the little bubbles. That's what the fizzing is. It's the carbon dioxide coming out of solution. So the tendency towards mixing, we need another quantity to measure here, and that's entropy. So we know that physical systems tend toward lower potential energy. We know that a ball will roll down the hill, not up the hill. If we look at this example here, we have two gases, argon and neon, in a container. They're separated. When we remove that barrier, the gases are going to mix, right? Because gas particles move in straight lines till they run into something, and so they're going to mix. They're actually going to mix much faster than a liquid with, pure water and salt water will mix. When these mix, does that change the potential energy of those particles? We haven't changed the temperature. The overall volume is the same. Number of molecules is the same. It does not change the energy. So these two gases mixing does not lower the potential energy. Why do they mix then, if it's not for lower energy? It's because of entropy. Entropy is a concept that's a little hard to get your mind around. There's several different ways you can define it. One way is it's a measure of energy randomization or energy dispersal in a system. So the idea is that the energy spreads out. That's a natural thing. It's called entropy. So when you have two ideal gases mixing, what happens is that the kinetic energy of each gas becomes spread out or dispersed over a larger volume. So if we go back to the picture, here neon has kinetic energy. Its kinetic energy is confined to half of the box. Argon has kinetic energy. Its energy is confined to half the box. When we allow them to mix, now neon's energy is spread out over the whole box, and argon is also spread out over the whole box. So we have energy dispersal. And that's what entropy is. That's an increase in entropy. So substances mix due to entropy, the pervasive tendency for energy to spread out whenever it's not restrained from doing so. Entropy also explains the transfer of thermal energy from hot objects to cold ones. So You put a pot of cold water on the stove and you turn the burner on. The burner's hot, the pot is cold. Do they stay that way? No. The thermal energy from the hot burner gets transferred into the pot, right? And the water becomes warmer. That's a spread of energy. It's an increase in entropy. Intermolecular forces can promote the formation of a solution or they can prevent it. So we've studied intermolecular forces. Here's a quick review. Dispersion forces occur between all substances. For nonpolar substances like heptane and pentane, those are the only forces of attraction between the molecules. Dipole-dipole forces occur between polar molecules, hydrogen bonds between polar molecules that have hydrogen bonded to fluorine, oxygen, or nitrogen, and then ion-dipole forces occur between polar molecules and ions. And dispersion forces are the weakest, and they go up in strength as you go to the right across here. So in order for a solution to form, we have to take into, we think about what's going on with these intermolecular forces. So there are forces of attraction between the solvent molecules. So like if we've got water, we've got hydrogen bonds and dispersion forces and dipole forces between the water molecules. We also have forces of attraction between the solute particles. If, say, you're dissolving sodium chloride in water, there's ionic bonds that attract the sodium ions to each other. And as a solution forms, there will be solvent-solute interactions. So salt water dissolving in water, then you're going to have ion-dipole forces, which are quite strong. So solution will form if the types of interactions between the solvent molecules and the solute molecules are similar. And so we have sort of a, I don't know what you call it. Like dissolves like. It's sort of a, what is that? Rule, it's not a rule of thumb. It's just a way of remembering. I don't know. Not feeling it today. Like dissolves like. And so that's what we think of when we think of making solutions. If the intermolecular forces present in the solvent and this solute are similar to each other, a solution will probably form. If they are different, it will not. And we have a term, miscible, that describes whether that two solute. This miscible means that two liquids are soluble in each other in all proportions. It's kind of a funny word if you think of miscible, mixable. They sound similar, and miscible means mixable. Mixable is not a real word. Alcohol and water are miscible. You could put, a teaspoon of alcohol in a cup of water, it'd mix up just fine. Or you could take a teaspoon of water in a cup of alcohol, and it would mix up just fine. Any proportion. Now, if you tried that with a solid in a liquid, it wouldn't work, right? If you took a teaspoon of salt and put it in a cup of water, that'd be fine. But if you took a teaspoon of water and put it in a cup of salt, it's not going to mix, right? Liquids that are miscible can be mixed in any proportion. So if we have solvent-solute interactions that are stronger than the solvent-solvent and solute-solute interactions, we can get a solution forming. If they're similar in strength, we can get a solution forming. If the solvent-solute interactions are weaker than the interactions between the solvent molecules and the solute molecules, the solution may or may not form. It depends on the difference. If those interactions are very weak, the solution's not going to form. When a solution forms, you have a gain in entropy. because you have this dispersal of energy. But in order for a solution to form, we have to break the interactions between the solvent molecules and between the solute molecules so that they can interact with each other. If the forces that are created in the new solution are much weaker, the gain in entropy might not offset the loss in energy. So you may not have a solution. So we should be able to answer questions like this, and this comes down to like dissolves like. And what we're looking for is what kind of intermolecular forces do these have? Are these things polar or nonpolar? So determine whether each compound is soluble in hexane. So what is hexane? It's nonpolar. What is it composed of? How would we figure out that it's nonpolar? It's carbons and hydrogens. So this name, hexane, this is one of those hydrocarbons. Hex meaning 6, so there's 6 carbons. And ane meaning this is a hydrocarbon with all single bonds. It's carbon and hydrogen. Carbon-hydrogen bonds are nonpolar. The molecule's nonpolar. So this is nonpolar. So then we look at the first one, water. Is that nonpolar or polar?
Polar.
That's polar. Is that going to mix with hexane? Nope. That will not mix. How about ammonia? Is ammonia polar or nonpolar?
Polar.
It's polar. Now you look at it, NH3, and unless you remember, because we've talked about ammonia quite a bit, unless you remember, you might not be able to tell, so you may have to look at the Lewis structure. And that lone pair on the nitrogen makes it polar. So that's also polar, not going to mix. How about propane? So here's the formula for propane. Is it polar or nonpolar? Nonpolar. So, do you think that'll mix with hexane? Yeah, it probably will. Hexane can be written CH3, CH2, 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 CH3. 1, 2, 3, 4, 5, 6. When looking at the formulas, this one looks a lot like this one. It's just like the big brother, right? They're both nonpolar. And so separating these molecules, separating those molecules, and then allowing these to interact with each other, there's not going to be much change in the energy, but you do have an increase in entropy from things spreading out. Hydrogen chloride, polar or nonpolar? Polar. This is a diatomic molecule. It's just hydrogen and chlorine. So if the bond is polar, the molecule is polar. Is that going to mix with hexane? No. Two nonpolar things will probably mix. Two polar things will probably mix. Polar and nonpolar, no.